Okay, let me start the recording. Okay, so again, in Calculus 1, you learn how to determine limits of different functions. And for those problems, for many of them, you used what are called limit laws. But in order for the limit laws to work, the limits, like if you say the limit of a product equals the product of the limits, that would hold if both limits exist. Okay, so the limit of the products equals the product of the limits, so long as both those limits exist. Well, in section 4.5, we deal with limits of functions that are more difficult to work with, where you can't apply the limit laws perhaps directly. And these are what are called indeterminate forms. Okay, so indeterminate forms, all right, indeterminate forms. So now let me see here. Hold on. Let me actually get my textbook out. So like this function here, this f of x function right here, which equals the log of x over x minus 1, that is an indeterminate form as x approaches 1. That is an indeterminate form. Why is that indeterminate? What happens to the numerator as x approaches 1? What happens to the log of x as x approaches 1? What does the log of x approach as x approaches 1? 0. That's right. That's right, Rodrigo. Because the log of 1 is 0. Okay. X minus 1. What does that approach as x approaches 1? So I'm looking just at the denominator now. We know the numerator, the log of x approaches 0 as x approaches 1, and Justice is right. The denominator also approaches 0 as x approaches 1. So what's happening here is you have a numerator going to 0 and a denominator going to 0 as x approaches 1. But can we say that 0 divided by 0 equals 1? I mean, is 0 divided by 0? Yeah, it's undefined. That's right, Sirfield. It's undefined. You can't cancel. You don't have 0 over 0. You have a numerator going to 0 and a denominator going to 0. And what that limit is going to be, the limit of this ratio of two functions both approaching 0, what that limit is going to be, we're not sure of. It's indeterminate. Okay, so and you've actually dealt with indeterminate limits before in Calculus 1. Like, for instance, this is a very famous one. If you have the limit as x approaches 1 of x squared minus x over x minus x, you learned about that you can factor. Because remember, we're not like putting 1 in for x. It's a limit. So we can factor the numerator and factor the denominator, and we see that the x minus 1 factors simplify out, and so the limit of x squared minus x over x squared minus 1 as x approaches 1 is going to be a half. Okay, and so that's something you learned you could do. That's that limit itself, is indeterminate. I mean, I want to say it the right way. X squared minus x, as x approaches 1, x squared minus x approaches 0, right? And the denominator, x squared minus 1, approaches 0 also as x approaches 1. So you have an indeterminate form there. You have a numerator going to 0 divided by a denominator going to 0. But we're able to get ourselves out of trouble, so to speak, because this problem, the numerator and denominator factor. Okay, and in Calculus 1, you learned about problems where that would work. Okay, but in this section here, for that problem where for that first limit there, the limit as x, the limit of the log of x over x minus 1 as x approaches 1, that you can't, there's no tricks you can do offhand for that you know of. Nothing in Calculus 1 you learned is going to help you with that limit. So we need to have a procedure to help us determine limits where we have an indeterminate form, where both functions f and g approach 0 as x approaches a. The question is, how are we going to come up with a way to handle this? And incidentally, you could also have a situation where you have the ratio of two functions f and g, and as x approaches a, the numerator function f goes to infinity, and the denominator function g goes to infinity. So you'd have infinity over infinity. That's another indeterminate form. That doesn't have to equal 1, you know, and so we need a way to help us handle this. Now, incidentally, you learned, again, in Calculus 1, they have an example there where you have the limit as x approaches infinity of x squared minus 1 over 2x squared plus 1. And for that problem, you can divide through numerator and denominator by x squared, and then you can find out that the limit's a half. Okay, how many remember doing that? How many remember doing that in Calculus 1? Sure. Okay, but we'll be encountered with situations where you can't do that kind of thing, where that won't work. So we need to use something of an approach called L'Hopital's rule. What is L'Hopital's rule? L'Hopital's rule says that if you have two differentiable functions f and g, meaning there you can take the derivative, okay, then and you know, of course, there are obvious you know, you can't have, well, you know, I mean, I don't want to get too technical here, but what L'Hopital's rule says is, if you have an indeterminate form where your numerator and denominator are both approaching 0 or both approaching infinity, then the limit as x approaches a of f of x over g of x is the same as the limit as x approaches a of the ratio of the derivatives, f prime of x over g prime of x. Okay. So the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime over g prime. That's what L'Hopital's rule is, and it's a very famous rule. And let me give you an idea of where that comes from. Okay. So here's a little picture. Here's a little picture where you have in Figure 1 two functions f and g, and you're interested in how the functions behave as x approaches a. So in Figure 1, as x approaches a, what does function f? What do both function f and g approach? What value do functions f and g approach in Figure 1? So look at that graph in Figure 1. What do functions f and g approach? What are the y values that they approach? The y values as x approaches a. 0. That's right, Adriana. That's right, Tina. So what's happening is you have two functions f and g approaching 0 as x approaches a. So f over g as x approaches a, the limit is an indeterminate form. But look at what they do here. They say, well, look, let's zoom in on these functions f and g near x equals a. Let's zoom in on that. If you zoom in on that, the functions start looking linear. And that's something you learned in Calculus 1. When very close to where x equals a, if you zoom in on those functions, the functions look like lines. And the equation of a line you can always find, because I mean, well, I want to say this the right way. Let me see here. You have a point. You have a point on both of the functions f and g, the point a0, and you can find the slopes of those tangents at the point a0 by taking the derivative of f and g. So you could get the equation of the tangent lines to f and g at the point a0. You learned how to do that in Calculus 1. Well, so instead of then, well, now we can approximate f and g with the two lines m1 times x minus a and m2 times x minus a, m1 and m2 being the two different slopes of those tangent lines, which you would, and if you look at the ratio of m1 times x minus a over m2 times x minus a, the ratio is going to be m1 over m2, which is the ratio of the slopes of the tangent lines, which is therefore the ratio of the derivatives of the tangent lines at x equals a. Hence, the limit as x approaches a of f over g is the same as the limit as x approaches a of f prime over g prime. That's what L'Hopital's rule is. That's the rule, and that's how they come up with the L'Hopital's rule. And this rule actually was discovered back in the 1600s by the Marquis de L'Hopital. He lived from 1661 to 1704. Well, they say it was discovered, they have a little, in the ebook, they have a little footnote here that talks about where the rule comes from. I'm wondering if they have it they have it in my book. I don't know, they ought to have it in your ebook, but that's anyway, that's anyway how the rule is named after. And they say the rule was discovered by John Bernoulli, who was another famous mathematician who lived about the same time, 1667 to 1748. But they name it after this Marquis de L'Hopital. So, all right, this is the L'Hopital's rule, and what I want to do is are there any questions so far before I move on to some examples with you? Okay, so, all right. All right, well then let's get to some examples here. Stop sharing here and bring up the examples. Okay, so take a moment to copy this example down. Take a moment to copy this example down. Okay, so how many remember maybe in Calculus 1 using a geometric argument to find this limit? Sometimes professors do that. How many have seen this limit before, maybe in Calculus 1? Okay, Snega remembers it. Rodrigo, it's Calom. So it's kind of a famous limit, kind of famous. And if you do use a geometric argument to find the limit, it's quite a bit of work. But we're gonna use L'Hopital's rule. Now, let me ask you, what kind of indeterminate form is this? Is it 0 over 0, or is it infinity over infinity? Okay, you have choice 1 and choice 2. All right, Felicity thinks 0 over 0. Tina thinks 0 over 0. And that's actually right, because the sign of x, as x approaches 0, the sign of x goes to 0. And as in the denominator x also approaches 0. So this means then we're gonna, it satisfies the condition of the first, it's the first indeterminate form, 0 over 0. So we're going to use L'Hopital's rule. Okay, and here's the solution. Okay, so by L'Hopital's rule, the limit as x approaches 0 of sine of x over x, okay, is going to be, and now I'm going to apply L'Hopital's rule. When I apply L'Hopital's rule, I put an h above the equal sign. And that's what I would expect you to do in your work for this kind of problem. You're telling me that you're applying L'Hopital's rule with the h. So the derivative of the sine of x is the cosine of x. The derivative of x is 1. And so the limit of the sine of x over x as x approaches 0 is the same as the limit as x approaches 0 of the cosine of x, and that gets you 1. How many found that easier than what they learned in Calculus 1 with the geometric argument? Okay, Rodrigo definitely finds it easier. Kahindi, Eric, Michael, yes. Yes. Cameron, yeah. So, all right. Well, now you have, a good thing here. All right. Thank you, Esther. Easier. Thank you, Snega. That's true. Are there any questions before we move to the next example? Okay. Okay. Well, okay. Let's take a look at this limit. Okay, give you a moment to copy it down. Okay. So initially, what people might want to do here is they might want to write this, thinking about Calculus 1. They might want to write this, and I'm trying to, write the best I can here. They might want to write this as the limit as x approaches infinity of x times the limit as x approaches infinity of the sine of pi over x. But the question is, can you do that? Is this even helpful? You can't. That's right. Good. Because you know for the limit of a product, and you have a product of two functions here, for the limit of the product of two functions to be equal to the product, this is a times here, the product of the limits, both limits have to exist. And the first limit, the limit of x as x goes to infinity, doesn't exist. So you can't do this. That isn't going to work. But is the indeterminate form here 0 over 0? Is it infinity over infinity? Or is it something else? It is neither. That's right, Tina. It's something else. What would it be? We got a product of two functions here. It's something else. So it's not going to be, good, Michael. It's going to be infinity times 0. The first term x goes to infinity as x goes to infinity. The second term, sine of pi over x, well, as x goes to infinity, pi over x goes to 0. The sine of 0 is 0. So you have infinity times 0. You have one term getting big times one. You have one function getting big times another function getting small as x goes to infinity. But can we say that infinity times 0 equals 0? Can we say that? I can say that 10 times 0 equals 0. But can I say that a term getting big, a function that gets large, times another function can I say that a function that's getting larger and larger and larger times another function that's getting smaller and smaller and smaller equals 0 or infinity? No, we can't. The two terms are fighting each other. So we have to use L'Hopital's rule to help us. However, we can't use L'Hopital's rule yet, because infinity times 0, okay, this limit is of the indeterminate form infinity times 0, and that's not L'Hopital's rule indeterminate form. L'Hopital's rule indeterminate form means I can apply L'Hopital's rule if I have 0 over 0 or if I have infinity over infinity. So what we have to do is we have to rewrite this function product so that I can apply L'Hopital's rule. All right, so let's go ahead and see how we do that. Okay, so I need, for L'Hopital's rule, I need a fraction where I have a function f on top and a function g on the bottom. So what I'm going to do is I'm going to multiply by 1 over x on the top and the bottom. So, of course, x times the sine of x is equivalent to x times the sine of x over 1. So I'll rewrite this limit by multiplying by 1 over x over 1 over x, which is equal to 1. Okay, 1 over x times the numerator, 1 over x times the denominator. And then that's going to give me this expression here. So we have an f here. And we have a g. And the question is now, is the indeterminate form 0 over 0 or infinity over infinity? What's the correct indeterminate form here? That's right, Justice. That's right, Tina. That's right. This is 0 over 0. The sign of pi over x, as x gets large, pi over x goes to 0. The angle goes to 0, and so the sign of pi over x goes to the sign of 0, which is 0. The denominator, 1 over x, also approaches 0 as x goes to infinity. So Tyreek says, why did I choose 1 over x? Well, yeah, I mean, how I tried it and it worked. That's my answer. Sometimes you don't know what to do, but you have to do something, right? And so I have to apply L'Hopital's rule. I need a function f divided by a function g. So it seemed to me easiest just to rewrite x times the sine of pi over x as the sine of pi over x divided by 1 over x. And now we've confirmed that we have an indeterminate form, and therefore, good question, Tyreek, therefore, we can apply, well, we're going to apply L'Hopital's rule, but I'm not going to apply it yet. Because when I take derivatives, I like to use the power rule as opposed to the quotient rule. So the pi over x, that angle there in the sign, I write it as pi times x to the negative first. And then 1 over x, I write as x to the negative first. Okay, so and now I will apply L'Hopital's rule and take the derivative of the numerator and denominator using the chain rule. Okay, so let me give you a moment to catch up here. Are there any questions so far? Okay. Okay, notice I put an H here because that's now I'm applying the L'Hopital's rule. So we use the chain rule for the numerator to differentiate the numerator. And you know, and you can see how easy it is to use the power rule. Does anything, I mean, now, does anything nice happen here? I mean, you know, here we are, we have this limit. Does anything kind of nice happen? Things cancel out. That's right, Colomb. The x to the negative second simplifies with the other x to the negative second. And so you're going to get the limit as x approaches infinity as of pi times the cosine of pi over x. The two negatives, the negative in the numerator and denominator, will be a plus. And now we can take the limit. Now we have a determinate form. This form here is determinate because pi over x approaches 0 as x goes to infinity, and the cosine of 0 is 1. And so we're able to find our limit. Okay, are there any questions on that? And this is like the, you know, what WebAssign is going to want, right? Let's see, Notnell says, how can we set it with 0 over 0 on the first step? Yeah, you don't. So how do we know 1 over x worked? So well, not now. This is the same question that Tyreek asked, essentially, but it's a good question. So you have to try something to. All right, I think I have a better answer here. So I know that to apply L'Hopital's rule, I need to have a function f in the numerator and a function g in the denominator. X times the sine of pi over x, I don't have a ratio of two functions. So what I'm going to do is I'm going to get a ratio of two functions. So I'm going to remove the x in the numerator by multiplying by 1 over x, and then I'll have 1 over x in the denominator. This gets me f over g, and I see right now that as x goes to infinity, f goes to 0 and g go to 0. So I get an indeterminate form. And so I can apply L'Hopital's rule. The problems are, cooked up so that they will work. Okay, they will work. And there aren't too many things you can do, you know. But okay, Nell, does that help you feel a little more comfortable? Excellent, excellent. All right, are there any more good questions before we move on to the next problem? So what I did, Tyreek, is at this step here, using L'Hopital's rule. So L'Hopital's rule, hold on here. L'Hopital's rule, remember, says that the limit, well, it says that when you have an indeterminate form, 0 over 0 or infinity over infinity, the limit as x approaches infinity of f over g equals the limit as x approaches infinity. Let me put this in red. Hold on, let me clear that. All right, so it's a good question. Here you have f. Here you have g. You have indeterminate form 0 over 0. So the limit of f over g is going to be the same by L'Hopital's rule. The limit as x approaches infinity of f over g will be the same by L'Hopital's rule as the limit as x approaches infinity of f prime over g prime, the ratio of the derivatives. Tyreek, does that make sense? Okay, good, good. Are there any other good questions? Okay, let's go to the next problem then. Here, well, let me give you a moment to copy this example down. Okay, so in this problem, well, you have the difference of the limit of the difference of two functions. Now, as x approaches pi over 2, 90 degrees, what's the tangent of x? What's the tangent of x approach? What happens to the tangent function at 90 degrees, pi over 2? If you look at the graph of the tangent, okay, we know that the tangent does this. It's undefined. So at pi over 2, okay, at pi over 2, and I know this isn't like the best graph, but I will label things appropriately. That's the origin there. This is the tangent of x. Y equals the tangent of x. And there's an asymptote there. So the tangent of x, well, it's undefined, Tyreek, that's right. But what does the tangent of x then approach at that asymptote, at pi over 2? And you notice we are approaching it from the left. You know, you have the little minus there. Infinity. So we got infinity. Good. That's right, Tina. That's right, Rodrigo. And the secant of x, remember the secant of x is 1 over the cosine of x, right? We think to our trig function days. So what does the cosine approach as x approaches 90 degrees? What is the cosine function approach? What is the cosine of 90 degrees? What is the cosine of pi over 2? Zero. That's right, Colomb. So the secant of x is actually approaching 1 over 0. So the secant of x is approaching infinity. So we have here yet another undeterminate form. This, we have an infinity minus infinity. But does infinity minus infinity equal 0? Not necessarily. It depends on the rate at which the one function, the secant of x, is approaching infinity compared to the rate at which the tangent of x is approaching infinity. That's what's going to determine what this limit is. But is this indeterminate form, infinity minus infinity, is this function, secant of x minus tangent x, in the right form to use L'Hopital's rule? Is it in the right form? No. L'Hopital's rule requires us to work with indeterminate forms of 0 over 0 or infinity over infinity. And so we're going to have to do something here. What we're going to do is we're going to write the secant of x as 1 over the cosine of x, and write the tangent of x as sine over cosine of x. Now the reason I'm doing that is I know that I have to do something. I have to try something. Well, I remember from trig days that the secant of x is 1 over cosine of x, and the sine and the tangent of x is sine over cosine of x. So why is this helpful? How is this going to help me? What can I do with these two fractions? We can subtract them. That's right, not now, because we have a common denominator. And by the way, even if we didn't have a common denominator, we could, if we needed to, we could get one, right? So sometimes, you know, here we are lucky. We have a common denominator. and we can just subtract the two functions. But if we didn't have a common denominator, which you'll see in some of your homework, you have to then just get a common denominator, you know. You've done that kind of thing before. Okay, so we're going to do that. Now at this stage, when we have the limit as x approaches pi over 2 from the left of 1 minus sine of x over the cosine of x, which indeterminate form do we have? Do we have 0 over 0, or do we have infinity over infinity? That's right, Rodrigo, 0 over 0. Because the sine of x approaches 1 as x approaches pi over 2. So in the numerator, you're getting 1 minus 1, which is 0. And then the denominator, the cosine function will approach 0 as x approaches pi over 2. So we do have the first indeterminate form, and we're going to use L'Hopital's rule. So we'll use it. We'll differentiate. So let me just kind of hold on here. One moment. So here's f, 1 minus the sine of x. And here's g, the cosine of x. Negative cosine of x is f prime. And negative the sine of x is g prime. So now, is this a determinate form? Is f prime over g prime determinate as x approaches pi over 2? Do we have it is, and by the way, if it were still indeterminate, we would have to use L'Hopital's rule again. Sometimes you have to apply L'Hopital's rule 2 or 3 times until you get the limit in determinate form. But yeah, this is determinate because the cosine of x, well, you know, the minuses can't simplify. Cosine of x goes to 0 as x goes to pi over 2, and the sine of x goes to 1. So that worked, and we have our limit. The negative, I like to say, Sergio, the negative simplified out. But yes, yes. Because in the numerator we had a negative, in the denominator we have a negative. Okay, good questions. Well, we did, oh, yes, Rodrigo says I left, hold on, there should be a little minus here. Thank you, Rodrigo. Good catch. There should be a little minus there. Absolutely, thank you. Let me fix that in my notes. How many like L'Hopital's rule? How many are fans of L'Hopital's rule? Uh-oh. Tina's not a fan? All right. Well, is there maybe one fan among you? I think when I show you this next problem, you're gonna be a fan. Okay. All right. Are there any questions before we move on? Justice is kind of right. Adriana says a little practice. It will make things easier for sure. Cologne says depending on the situation. Sure. Well, we wouldn't use L'Hopital's rule if we need to, but all right. Well, let's go to this problem here. Not this one. I want to go to the next one. Hold on. Boop. Okay, let me give you a moment to copy that down. Now for this problem, we're looking at the limit as x approaches 0 from the right of 1 plus the sine of 4x, 1 plus the sine of 4x raised to the cotangent of x power. So let me ask you, what does the sine of 4x approach as x approaches 0? I mean, 4 times 0 is 0. So what would the sine of 4x approach? If you graph the sine of 4x function, that would have what? A period of pi over 2. But, I mean, what would the sine approach? That's right, it approaches 0. So you have 1 plus 0 here. So you have 1, okay, raised to some power. Now the cotangent of x, how's the cotangent of x defined? Cotangent of x is equal to, think of your trig days. How's the cotangent defined? It is the cosine over the sine. The tangent would be the sine over the cosine. So the cotangent is the cosine over the sine. But what's happening here is, as x approaches 0, the cosine is going to 1. The cosine of 0 is 1. But as x approaches 0, the sine approaches 0. 1 over 0 is infinity. That's not indeterminate. In other words, the cosine is approaching 1 in the numerator, the cosine of x, but the sine of x is getting smaller and approaching 0. So 1 over 0 is, I'm going to say it the right way. It's not like, remember, it's not like you're taking 1 and dividing it by 0, because this is a limit, right? But what you're doing is you have a numerator approaching 1 and a denominator approaching 0, so the ratio has to be approaching infinity. So this is your indeterminate form for this problem, 1 to the infinity power. That is yet another indeterminate form. We don't know if that equals 1. We don't know if that equals infinity. We don't know what that equals. Okay, it's indeterminate. Okay, it's indeterminate. And again, it depends on how fast 1 plus sine of 4x approaches 1 relative to how fast the cotangent of x approaches infinity. But unlike the other problems we had, we can't easily manipulate this limit. We can't easily manipulate it. What makes it hard? What makes this limit like more difficult than the 3 previous limits we looked at? What makes it hard? So I'm looking now at the actual function here. Well, there's no square root in here. It's 1 plus the sine of 4x raised to the cotangent of x power. It's definitely, I agree with Rodrigo, it's definitely that power there, the cotangent of x, that's making our lives complicated. So we're going to do a little trick here. What we're going to do is we're going to find the limit of the log of this nasty function, and then we'll manipulate that limit to help us. So let me just show you what to do here. What we're going to do is we're interested in finding the limit as x approaches 0 from the right of 1 plus the sine of 4x raised to the cotangent of x power. I'm going to define 1 plus the sine of 4x raised to the cotangent of x power to be equal to y. I'm going to call that y. And then what I'm going to do is I'm going to take the log of y. And you're going to see why. But let me give you a moment to copy that down. Okay. So think about your log rules. What's the log of a to the bth power equal to? What's the log of a to the bth power going to equal? Good, good, everybody. B times the log of a. So we're taking the log of y so that we can get that cotangent of x out so it's not a power anymore. Okay. So so the limit as x approaches 0 from the right of the log of y would be the limit as x approaches 0 from the right of the cotangent of x times the log of 1 plus the sine of 4 times x. Give you a moment to copy. Give you a moment to copy that. Okay. So of course, we're interested in the limit as of y as x approaches infinity. You know, we're interested, I mean, this was our original problem, right? Find the limit of y as x approaches 0 from the right. But we're going to first find the limit of the log of y as x approaches 0 from the right. Now, what we're going to do here is I got to get a fraction. I got to get an f over a g. So let's say that I wanted to call my log of 1 plus the sine of 4x my f function. How could I get a function g in the denominator from the cotangent of x? How can we, the cotangent of x is the cosine over the sine, but it's also good, Rodrigo and Tina, it's also 1 over the tangent of x. So I can write my limit as the log of 1 plus the sine of x. Okay, that's my f over the tangent of x. That's my g. And the question is now, do we have an indeterminate form that we can use L'Hopital's rule on? Is this indeterminate form, f over g, going to be 0 over 0 or infinity over infinity? What do you think? Tina thinks 0 over 0. Rodrigo thinks 0 over 0. Well, you're right. This, because the tangent in the denominator, as x goes to 0, the tangent goes to 0. And 1 in the numerator, 1 plus the sine of 4 over x, as x goes to 0, 1 plus the sine of 4 over x approaches 1, sorry. 1 plus the sine of 4 over x approaches 1 as x approaches 0, and the log of 1 approaches 0. So we have an indeterminate form, 0 over 0. We can apply L'Hopital's rule. Okay, and so now we have f prime over g prime. And again, I just applied, what rule did I use in the numerator to differentiate the function f? What special rule? When I took the derivative of the log of 1 plus the sine of 4x, that's right. That's right. We used the chain rule. So the question is now, is this form here, is f prime over g prime, is it in determinate form? Is it in determinate form? That means can I figure out the limit as x approaches 0? And the answer is yes, we can. We can just put in 0 for x everywhere. And we'll see as x approaches 0, the limit is going to be 1 over 1 plus 0 to 1 times 4, all divided by 1 squared. And so we get 4. So the limit as x approaches 0 from the right of the log of y equals 4. But is that our final answer? Is that what we're looking for? No, it's not what we're looking for. What we're looking for, good Snega, good Tina, what we're looking for is the limit as x approaches 0 from the right of y. And actually, Tina's suggestion's good. To get this limit, we're going to exponentiate our limit, because e to the log of y equals y. And you will find it will equal e to the fourth. But let me go to the next page and show you. So remember, this is what we want to find. Are we good so far? Are there any questions? Okay, all right, good. Well, so again, this here was our original problem. Finding the limit as x approaches 0 from the right of 1 plus the sine of 4x raised to the cotangent of x power. But that was equal to the limit of y, because we defined y to be 1 plus the sine of 4x raised to the cotangent of x power. But here's what's really cool. I can write y as e times the log of y. But we know the log of y, as x approaches 0 from the right, is equal to 4. So our final answer here is going to be e to the fourth. So we took the log, but then we exponentiated the log to get our answer. Pretty clever, huh? How many kind of think that's cool? Yeah, Tina likes that. Eric likes it, sure. All right. So what we did was we know that as x approaches 0 from the right, the log of y approaches 4. That's another way to write this. As x approaches 0 from the right, the log of y approaches 4. Well, we wanted the 1 plus the sine of 4x raised to the cotangent of x power. This here, by virtue of the fact that we let y be equal to 1 plus the sine of 4x to the cotangent x power, that means that 1 plus the sine of 4x raised to the cotangent of x power is the same as e to the log of y, right? But we know as x approaches infinity, log of y approaches 4. Log of y approaches 4. So the limit as x, as x approaches 0 from the right, the log of y approaches 4. So that means as x approaches 0 from the right, e to the log of y would have to approach e to the fourth power. Yeah. Good, Sirfield. Sirfield is comfortable. I mean, as x approaches 0 from the right, e to the log of y, it's kind of nice when I write it out like this, e to the log of y would approach e to the fourth. I mean, what else can it do? It has to approach that. And so our final answer is e to the fourth power. All right, are there any questions on that? Okay, I'll stop the recording here.